Okay, good morning, everyone. Let's see, before we start logistics, almost everybody who wrote to me about having trouble getting into Wiley Plus was someone who had paid for both semesters at the beginning of the fall semester. And you should now, Wiley has opened up the course for you, and you should now be able to get in. So try it and let me know if it doesn't work today. Okay, but it should be working. Let's see. Oh, so I'll put this in Canvas, but tentatively I've decided on office hours, which will be via Zoom, of course, will be Fridays from 1 to 2, 1 to 1:50, and Mondays from 1:30 to 2:30, and I'll post that in Canvas. If you want to talk to me at any other time, shoot me an email and we'll set up a Zoom chat to talk at a mutually convenient time. Okay. So last time we talked about, so today we get to start talking about the thing that's going to be the main focus of the course, which is electric field. But before we do that, last time we reviewed electric force and the use of vectors in calculating electric force. So let's just review slightly before we go on. So I'm going to share my screen. And let me find the chat, which is always hidden somehow. There we go. So here's a question about electric force. So a sodium ion, which is sodium plus 1, so sodium that's lost 1 electron and has a charge of plus E, exerts a force of 3 × 10⁻⁸ newtons on a proton that's some distance d away. If we move this sodium ion a distance 3d away, what would the magnitude of the force on the proton be? Okay, let's see what you said. Well, we're just about evenly divided between answers 3 and 4. And they're not both correct. So let's see what is correct here. Gonna switch cameras. Okay. So last time we talked about the electric force. And we found that the force exerted by one charged particle on another was equal to a constant 1/4πε0 times the charge of particle 1, the charge of particle 2 over the distance squared, and the direction was given by the vector r hat. . Now, we're interested in magnitudes here. So we just want the magnitude of this, and so we're going to take the magnitude of that. The magnitude of a unit vector is always 1. So here we have, so the force, the original force is Q1 times Q2 over some distance d squared. It's a constant, Q1, Q2 over d squared. The force at a distance 3d is going to be 1 over 4 pi epsilon 0 Q1, Q2 over the quantity 3d squared, right? And so that gives us 1 over 4 pi epsilon 0 Q1, Q2 over 9 d squared. So it's equal to 1/9 the original force. That's what a 1 over distance squared force does. So therefore, it's going to be equal to 3 times 10 to the negative 8 newtons divided by 9. So it is not answer 3. It is in fact answer 4. And that's something to watch out for. This 1 over distance squared dependence means that when you double the distance, the force goes down by a factor of 1 over 2 squared. When you triple the distance, the force goes down by a factor of 1 over 3 squared, okay? So that's an important thing in reasoning about forces. Okay, one other question, which you should be able to think about after yesterday's recitation, Tuesday's recitation. Okay, so we have an alpha particle, which, as you know, is 2 protons and 2 neutrons. It's a helium nucleus, right? With no electrons. It has a charge of plus 2e, where e is the charge of 1 proton, 1.6 times 10 to the minus 19 coulombs. And it's a tenth of a meter away from a single proton, which has a charge plus e, so half the charge of the alpha particle. And the question is about the magnitudes of forces. Which statement about the magnitudes of the forces that they exert on each other is correct? So the first answer is the force on the proton by the alpha particle is equal to the force on the alpha particle by the proton. Second answer is the force on the proton by the alpha particle is bigger because the alpha particle has more charge. The third is the force on the proton by the alpha particle is smaller. And overwhelming, you say that the force on the proton by the alpha particle is equal to the force, equal in magnitude to the force on the alpha particle by the proton, and that's absolutely correct. So you nailed that one. So equal and opposite, and we see this from the form of the force law here, that the magnitude of these forces come out to be the same. The only thing that's different in this equation is actually going to be the vector r hat, which is going to point in the other direction. So the magnitudes of the forces are exactly the same. Awesome. Okay, what I would like to try to do now is to actually show you a demonstration. And I got this to work last night, so let's see if I can get it to work today. So here is some equipment that we'll be using in lab. This is just a little light bulb. It's a little incandescent bulb from an old style flashlight. Okay, before all flashlights had LED bulbs. Yeah. And this device is just a socket for the light bulb to make it easier to connect wires to it. So we're gonna screw the light bulb into the socket. And then I just have a couple of wires here. I have a red wire and a black wire with clip leads on the end, and I've just coiled them up so you can see both ends while I'm doing things with them, but there's nothing special about them being coiled up. Just kind of. And what I'm going to do is connect a red wire to one prong of the socket and a black wire to the other connection, and nothing happens. The light bulb doesn't go on, and you're surely not surprised because you didn't expect it to go on. Now, presumably, if we use a battery, this is just an ordinary 1.5 volt battery. This is a D cell, so it's fat. And again, it's in a battery holder just to make it easy to connect my clip leads to it. So I'm going to connect this lead to one end of the battery, which is labeled minus, and this lead to the other end of the battery, which is labeled plus. And you can see that the light bulb now lights. Okay, so again, you're not surprised. You know that you need a battery to light a light bulb. Okay, so I'm going to disconnect it from the battery. And now what I'm going to do is I'm going to plug in this device, which is a box with a metal. This is just an aluminum bar, basically, here. And the only thing that's going to happen when I plug it in is the red light will go on. So I'm going to plug that in. The red light's on, so now this device is on. And put it here. And now what I'm going to do is just hold my light bulb not connected to anything right here near this, but not touching it. So let me move the camera a little bit to see if I can get in a little closer. Okay, so here's my light bulb, not connected to anything. I'm holding it near this, and I think you can see that the light bulb is actually on. Okay, and if I rotate the light bulb, rotate this, the light bulb goes out. If I move it farther away, the light bulb gets dimmer and goes out, but as I move it closer, the light bulb gets brighter. But somehow, with using, yeah, the leads are not attached to anything. Okay, so these wires here are not connected to a battery. They're not connected to each other. They're just connected to the light bulb. Oh yes, the wires. Yes, the wires do have to be attached to the light bulb to make this work. Let's see. Let me try it. stand in a different place. Yeah. So I'll try to stand behind it, in fact. Okay. So it's on. You can see that. If I turn this, it goes out. If I turn it this way, it goes on. If I move it over here, the light bulb goes out. If I but here, and so do we have to have the wires attached to the light bulb to make this work? So I took the wires off. I'm going to hold the light bulb here, and you can see that it's not lighting. Okay. So the light bulb doesn't light if I don't have those wires attached, but if I reattach the wires, and then I reattach the wires, hopefully with decent contacts. And if I haven't burned out the light bulb, yes, there it goes again. So it's now on. Okay, so the wires did have to be attached, but they're not connected to anything. They're just dangling in the air. So this is kind of interesting. That's not something we necessarily expected. And this course kind of has a storyline. And the storyline is that we will, throughout the semester, learn more and more until we can explain in great detail exactly what was happening at a microscopic level inside these wires and inside the light bulb, both when it's attached to a battery and when it's not attached to a battery, but when I have this device plugged in and I hold it near the device. And we'll also be able to explain why the orientation mattered, why when I held it this way it lit, but when I held it that way it didn't. Okay. So that's the goal of the course, and it's going to take us most of the semester to get there. But piece by piece, we will put this story together. There certainly was a distance dependence, wasn't there? So the distance dependent. I mean, you saw that. I think you saw the light bulb got dimmer when I moved it away. Well, that's a possible. Witchcraft is a possible explanation, but we're gonna look for fundamental physics principles that will actually help us explain those things. And to do that, we're going to need to talk about electric field and magnetic fields too, actually. So let's talk about electric field. And in fact, this idea of distance dependence is a really key thing. So let's talk about distance dependence. Okay. So we know that both electric and gravitational forces act at a distance. We talked about the 4 fundamental kinds of interactions last semester, and the strong force that holds protons and neutrons together in the nucleus is practically it's very much like a contact force. Okay, they need to be touching essentially for this to work, and as is the weak interaction. But both the gravitational and the electric interactions actually occur at a distance. So So, and that's that distance dependence that we were talking about in that first multiple choice question here, where the force fell off with distance. Now, how does this actually work? So we have the Earth here, we have a spacecraft here. The Earth exerts a force on the spacecraft, even though it's not actually in contact with the Earth. But how does it do that? How does the Earth doesn't know that the spacecraft is gonna be at this location in 2 minutes. So how does it know how to do that? Information can't travel faster than the speed of light. Nothing can travel faster than the speed of light. That's our universal speed limit. So how does this work? And the idea that physicists have come up with to explain this, to describe this, is that an object with mass, so an object with mass m, fills all of space out to infinity with a gravitational field. And you've certainly heard that word, gravitational field, right? So there's a gravitational field everywhere in space surrounding a massive object. And the field has a magnitude. It gets smaller as one travels away from it, but it also has a direction, in the sense that an object here is going to feel a force in a different direction from an object here. So we envision this field as being a vector of consisting of some sort of vector quantity that has a magnitude and a direction. And the direction for a gravitational field is the direction that another massive object would experience a force and begin to move. So there'd be a gravitational field everywhere in space, and I'm drawing it in a 2D slice around this massive object. Say it's the sun, whatever, the Earth. And of course it would get smaller as we got farther away. And it's sort of like a giant, you can think of it as this giant 3D spiderwebby kind of thing that just lies in wait for masses to come along and be affected. So it's always there, it's invisible, it's not something we can detect with our eyes, so we'd have to put a massive object somewhere and see what happened to it. But that a massive object fills space with a gravitational field, and we would use, so we might use the symbol little g with an arrow over it to say this is a gravitational field. Well, I can't argue with invisible space spiders sounding a little mysterious, but and so direction, okay, I'm not a Marvel Comics expert, so I'm not a DC Comics expert either, so, but direction of, is the direction a massive object would start to move. Okay, so the gravitational force and the electric force are similar. So we postulate something very much like that for electrically charged particles, but with a slightly more interesting twist. If we have a positively charged particle, this positively charged particle is surrounded everywhere in space by an electric field that's associated with this charged particle. We use the symbol capital E with an arrow over it. And I drew it wrong. So a positive charge is going to make an electric field that points away from it. And so the definition of the direction of electric field is the direction that a positive charge would start to move. So it's the direction of the force on a positive charge if there was one there. But notice that this field is there whether there's anything to experience it or not. It's just filling space, waiting for something to happen. So all around a positive charge, there'd be an electric field pointing away from it, basically. A negative charge, on the other hand, over here, here's a negative charge. Since a positive charge would move toward a negative charge, it appears that the electric field made by a negative charge must point toward it everywhere in space. So if we have an electric field measuring device, and we would need one to measure electric field, and we'll talk about how we do that. So what's the difference between force and field? Great question. So the force that something is going to experience depends on the field. So if there's a field at some location in space, let's pick this one, and we put a proton there. So the way you measure electric field is with a test charge. You have to put a charged particle there and see which way it moves. And you want to use a really small charge because you don't want it to affect the position of what we call the source of the field. So this is the source. So if we put a proton, let's say we'll put a proton right here, and we measure the force, and we attach a spring to our proton so it can't go very far, but so we want to see which way the spring stretches, which way the proton starts to move. And we find that there's a force on the proton this way. But if we put a proton out here, we'd find a force in the same direction, but it would definitely be a lot smaller. So the force on a charged object by an electric field depends on the magnitude and direction of the electric field. And in fact, there's a really simple relationship which we can write this way. So force on some object on our system is equal to the charge of our system. So if we had an alpha particle, it would experience a bigger force than the proton, multiplied by the electric field, which is due to the surroundings. And yes, by convention, we established we've decided that the direction of the electric field is the direction that a positive charge would experience a force. So if we put our positive test charge somewhere, then it would experience a force that way. And so let's see how that comes out of our equation here. So here's a location where there's an electric field pointing that way, and we actually don't know what the electric field is due to. It could be a positive charge located over here, but it also could be a negative charge located over here. The field's exactly the same. We can't tell the difference. So to measure the field, we put a little positive, our little positive test charge here, and we discover that it feels a force that way, so there must be an electric field that way. Okay, so I think your question is really about field, because field and force are different, and they have different units here, right? So force has units of newtons, right? And charge has units of coulombs. So electric field must have units of newtons per coulomb. This is the force per coulomb, the force that you would experience, if an object would experience if it were there. And so field and force are different, and it's going to take us a minute to get this terminology right, but there are no synonyms in physics. So we need to be careful to say field when we mean field and force when we mean force. So the electric field, how do we know, why do we draw the electric field near a negative charge as pointing in to the negative charge? Well, it's because if we put our little proton on a spring here, it would definitely start to move that way. That would be the force on a proton. It would be moving toward the negative charge. So we deduce that the field associated with a negative charge has to point toward the negative charge, just like the field associated with a positive charge has to point away from the positive charge. Okay, now this is an equation that is important and you're going to need to know. And it's actually pretty powerful, because it turns out that if we knew the value of an electric field at some location, we knew E, we measured it, we could predict the force on any charged object that was at that location. So if we know here that, let's pick some location in space. Here's our location. We call the location at which we measure the field, or which we want to measure the field, the observation location. At some location in space where we want to measure the field. And let's say we've measured the field with our little proton on a spring, and we knew the force on the proton, so we could calculate the value of the field. And we found that the field, the electric field here at this location in space, had a value of 6,000, 4,000, 0, since we're drawing this in the XY plane, newtons per coulomb. So why are we using a positive charge as the reference? We had to use something. It basically was a choice by convention, but all the algebra works out correctly here too. So notice that if we define E as being in the direction a positive charge would move, what would happen if we put a negative charge here at a location where there's an electric field in that direction? Well, the electric field still has the same value, but now this number, the charge of the system, that becomes negative. And we're multiplying this electric field by a negative scalar, the charge on the negative charge, and so the force is going to end up being in the opposite direction, so algebraically it all works out. Coulomb is a capital C. Well, E is not just the direction, it has a magnitude too, right? So a stronger field makes a bigger force. So the direction of E is the direction, it's the direction of E that's the direction a positive charge would move. The magnitude of E has to do with the magnitude of the force on this positive charge. So let's say we know the electric field at this location. We don't have to know what made it. It could be a single charge, it could be lots of charges, and the world is full of charged particles, so we're going to find that we're often in a situation where we need to know the electric field that's made by lots and lots of charges. But for now, we'll just talk about field of one charge. So what's going to happen? Suppose we put a proton here. What would the force on a proton be? Okay, well, we calculated using our equation F equals QE. So the force would be the charge of the proton, which is 1.6 times 10 to the minus 9 coulombs, capital C, a scalar times the value of the electric field, which is a vector, 6,000, 4,000, 0 newtons per coulomb. And we'd get a force of 9.6 times 10 to the negative, whoops, this is a 19. Negative 16, 6.4 times 10 to the negative 16, 0 newtons. But what if we put something different there? So suppose we put a force on a little teeny plastic sphere that had a charge of -6 microcoulomb. So micro is 10 to the minus 6, right? Well, all we have to do to calculate that is multiply -6 times 10 to the minus 6 coulombs times the electric field. And that's going to give us a force of negative 3.6 times 10 to the negative 2, negative 2.4 times 10 to the negative 20 newtons. And it's in the opposite direction. Okay, so the force on the proton, but the force on -3 microcoulomb charge is in the other direction. And that just falls out of the algebra. We multiply by a negative number, so the components of this vector are negative. Okay, so let's see if we can answer a question. So we place a proton at location A, and we know that we observe that the proton experiences a force in the direction shown by that black arrow. What can we deduce the direction of the electric field at location A to be? So overwhelmingly, you said the direction is 8. And that's absolutely correct. So the direction of the electric field is the direction in which a proton would experience a force. And since the force is in that direction, we know that at location A, where the proton is, there must be an electric field in the same direction. Now, one of the things when we draw fields and forces, we need to be fairly careful about where we put the tail of these arrows. And the reason is that a field at one location in space has a completely different value from a field in another location in space. So we really want to make sure that we're indicating the location in space that we're talking about when we. So let me show you a Python program. So what we've got here is a positive charge making an electric field everywhere in space. And what's depicted in this program is the electric field at points on a grid, right? Because if we tried to draw it everywhere, we just have a massive orange and we couldn't see anything. So we see that at locations near the positive charge, the electric field is large. At locations far from it, it's very small. And if we move the charge, the field everywhere changes. Now, how does the field know to change? So this field exists throughout space, and we're moving the charge around, and the field everywhere changes. Now, you might wonder how it can do this. Could it do this instantaneously? And the answer is, well, it actually can't. So it turns out that if we move the charge here, information about the location of the charge only travels with the speed of light. And so it gets to locations close to the charge before it gets to locations farther away. And that's an interesting feature of this. So this is our invisible orange web of vectors everywhere in space, waiting for some charge to come along and feel a force. Okay. So let's try one other question. Okay. Okay, so this is an interesting question about what experiences the change. And I think we need to think very carefully here about system and surroundings when we're thinking about this question. So in a certain sense, when we talk about an electric field due to something, and this was the electric field made by this positive charge, this charge we call it the source of the electric field. Okay, so the source charge really means the surroundings. And so this is this part of the surroundings. This is the thing that's responsible for creating this field. Okay. Now, yeah, that's about right. Okay. Now, so far, nothing is experiencing a force. There's nothing here to experience a force. So all we've got is a field. So this source charge moved, and probably it moved for some reason. Either it actually already had some momentum, or somebody picked it up and moved it, or it got a kick, whatever. I mean, yes, it's in the program I was dragging it. Okay, so I was moving the charge, so I was forcing it to move, and that was affecting the field at other locations. Now, it does make sense to ask, though, if this electric field that's due to this positive source charge, does this field affect this charge? Is the source charge affected by the field? By its own field, let's be clear. Well, how would it be affected? In what direction could it exert a force on itself? There's no obvious direction a particle could exert a force on itself. So it's just like an object isn't gravitationally attracted to itself. It's not electrically affected by itself either. So no. So no, it doesn't affect itself. Now let's go back for a minute then to this program. So here's one of these cases where we need to be careful about terminology because there aren't any synonyms. So if I drag this charge to a new location, wherever it is, it's making a field that is whose change is quicker when a location's close to the charge and slower. It's slower to get the information change when it's farther away. But we need to distinguish between the idea of charge and the idea of field. Okay, so the field is this influence. It's this thing that will create a force on something, some unsuspecting charged particle that comes along and finds itself at some location. So if a charged particle came along, a proton came along and sat at the location where my cursor is, it would feel a force in that direction, right? But the field itself is a different thing from charge. The field is not, we can't say the field is charged. That doesn't make any sense. So the only thing that has charge is a particle, and we know what charged particles are. We have protons and electrons and antiprotons and positrons and various kinds of muons and pions and delta particles and whatnot. Those are the things that have charge. The field itself is not a particle. It's this invisible thing. It has no mass. it's just out there as a field. And if we're somewhere at this, we're somewhere here just observing fields, we may not even know we may not be able to see the source charge if we're far enough away. So we might even not know whether it's positive or negative. It does raise an interesting question, though, which is this. Well, let me not share the screen for a minute. Let me just talk about it for a minute. So suppose I have a charged object in this hand, and it makes an electric field all around it. So let me have a charged object. Here's my charged object, and that's our source charge. And it makes an electric field everywhere. Let's say it's a positive charge. So when I take my proton on a spring and I put it over here, I find that the proton wants to move that way. So I deduce that at this observation location, the electric field is going that way. And let me say, okay, so now I'm about, the observation location is about 30 centimeters away from the location of the charge, right? So about 1/3 of a meter. Okay, now let's say I move this charge very suddenly. Somebody gives it a kick. So it moves down to here. Okay? What is my proton on a spring going to detect? Well, instantly, nothing. We have to wait for a nanosecond before it says, oh, I see that the field has changed direction and because this charge moved. So it takes this information about the source of the charge moving only travels at the speed of light. And so if we were, let's imagine that we're a meter away now. My observation location is a meter away. I move the charge, and it takes 1 nanosecond, 2 nanoseconds, 3 nanoseconds before the proton says, oh, the field now points that way. This is called retardation. And it's a consequence of this universal speed limit, which is 3 × 10⁸ meters per second. Okay. So let's see if we can figure out whoops, I didn't mean to do that. Sorry. Let's do that. See if we can figure out an equation that describes the electric field due to a single source charge. So what is the electric field of a single point charge? So we have some charge Q⁻₁. This is our surroundings. It's the source of the field. And we have some charge Q⁻². That's our system. And we know that from what we know about electric forces, that this force on 2 is going to be equal to 1/4πε0 Q1 Q2 over the magnitude of the vector r squared r hat, where the vector r, and this is something you really, really, really have to get straight, goes from the source charge to the system that's being affected. But we also know that the force on 2 is just equal to the charge of 2 times the electric field made by the source. So electric field due to the charge 1. So combining those two equations, it looks like the electric field due to 1 is just the force on 2 divided by the charge of 2. So the electric field due to a single point charge is going to be 1 over 4 pi epsilon 0 q of that source charge over the magnitude of r squared r hat. We're talking about the observation location. So here's our source charge q1. Here's our observation location. And the vector r is pointing from the source charge to the observation location. So r is equal to the observation location minus the source location. And so we can predict the electric field due to a point charge at any location in space we want to, just by doing that calculation. So let's see what that looks like. Okay, so here we have a point charge. Seems to be a positive charge. And what we're doing here is using these orange arrows, and I will typically use an orange arrow to represent electric field, represent the electric field at what location? The observation location is at the tail of the arrow. We put the arrow, so we calculate the electric field at this location due to that positive charge, and we find that it's pointing directly away from the charge, and it has that magnitude. Over at this location, we find that the electric field points in the plus x direction. It's that magnitude. At an observation location that's farther away, in fact, twice as far away, so this is one distance, these outer ones are twice as far away, we see that the electric field is down by a factor of 4 because of that 1 over distance squared dependence. And of course, it's not just true in the plane, it's true everywhere. So if we add observation locations in the YZ plane, we find the same pattern, and we could add observation locations all over the surface of a sphere, and we'd find it pointing away. So think for a minute about what's going to change if I make the charge negative instead of positive. So let's replace our negative charge, our positive charge, with a negative charge. And we see that the direction of the electric field created by this source charge, so the electric field associated with this source charge, changed to point toward the charge because that's the direction our proton on a spring would move if we put it at the observation location. So at this observation location, now the electric field points toward the positive charge. At this observation location up here, the electric field points toward the positive charge, but it's only a fourth as big because it's twice as far away. So again, very importantly, the tail of the vector representing the field is drawn at the observation location. And again, we can add more observation locations in another plane just to give us the sense that there's really this spherical symmetry about this whole field thing. Okay. So let's calculate the electric field due to a point charge. So let's make our source an electron. So we'll have an electron. So does the field extend to infinity, but the distance is too great to necessarily? Yeah. So the field, the electric field, does extend infinitely far. Okay, there's no limit on how far it goes. However, you saw that 1 over distance squared means that the magnitude of the field falls off very fast. And so as you get farther and farther away, the magnitude gets smaller and smaller to the point where it probably isn't going to have a huge effect. It will have a very tiny effect on something. Now, if you had an electron making an electric field and a light year away, the field due to that electron would be very small. But suppose you put a proton there and there was nothing else around that was charged within many light years. So there are no other forces acting on that proton. Well, the proton would feel a tiny force, and it would very, 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 very slowly start to approach the electron. It would take many, many, many years for this to happen, but it's not zero, okay? But if there's any other forces acting on that proton, then it probably would be more strongly affected by those. So here's our electron, here's our observation location. This is our source charge. And we want to calculate the electric field of this electron at this observation location. Okay, so to do this, we're going to use our equation for the electric field of a point charge. We see the electric field is 1 over 4 pi epsilon 0 q of the source over the magnitude of r squared, r hat. And notice that this equation is actually could be written this way. We could write the electric field as a function of r, the vector r, because of course that is what we're calculating. This functional dependence is actually implicit. We just don't write it because it's a little simpler. There's less writing. But implicit in this equation, which is the second equation that you're going to need to memorize and have burned into your brains, implicit in this equation is this dependence on r, that it varies with r. So if we draw the vector r from the source to the observation location, and let's say that in this case our vector r, it's obviously in the negative x direction, so let's say it's -1 times 10 to the -6, so 1 micrometer, 0 meters. Then to calculate the electric field due to the electron at that location, We have a 1 over 4 pi epsilon 0, which is a 9 times 10 to the 9 Newton meters squared per Coulomb squared. We have the charge of the source charge. It's an electron, so it's a minus 1.6 times 10 to the minus 19 coulombs. We have the magnitude of r squared. Well, we can tell by inspection that the magnitude of r is just 1 times 10 to the minus 6 meters. So we have 1 times 10 to the negative 6 meters squared. And again, by inspection, we can see that r hat is just negative 1, 0, 0. So we'll multiply by negative 1, 0, 0. And when we work that all out, we get an electric field at that observation location of plus 1440, 0, 0 newtons per coulomb. And so if we were going to draw it, we would draw the electric field in the plus x direction, pointing at the electron. I've offset it slightly just so we can. Okay, so now we would be able to calculate the force on any charged object we wanted to put at this observation location. We could put a proton there, we could put an alpha particle, we could put a chloride ion. Once we know the value of E, we can calculate a force using our other equation, force on this system. So again, force on the system is equal to charge of the system, whatever we put there, times the electric field due to the surroundings. Now here's a factoid which we will not be able to prove until chapter 3. It turns out that, chapter 15, a macroscopic spherical shell of charge, so what does that mean? It just means that there's one layer. Okay, so you could have a solid object here like a marble, say, a glass marble. And if you had a uniformly distributed charge all over the surface of this object, I think factoid gets used in other ways too, like a fact that isn't linked to anything else is sometimes called a factoid. But so fact, if you like, a uniform with so this is just this little layer of charge. So it looks like the charge itself is on the surface of this thing. There's no charge inside. So that's what it means by a spherical shell of charge. Behaves electrically like as if it were a point charge at its center. So if Superman, you had this charged marble because you'd rubbed it on your sweater, actually on a silk handkerchief. You rubbed a glass marble on a silk handkerchief. It's got a positive charge uniformly distributed all over it. And we'll talk about how that can happen in chapter 14. This actually looks to an observer some distance away as if it was just this positive point charge located at the center of this thing. And that's convenient partly because it lets us do calculations for things other than just things that really do look like point particles, like protons and electrons. So the question is, does human skin have a macroscopic spherical shell of charge? Well, there's two layers to that question. We're not spheres, so no. Okay, we're a funny shape, so we're more like, I don't know, gingerbread man, right? Okay, we look like a gingerbread man. So that's definitely not a sphere. So now, could we have charge all over our skin? Well, that's a really good question, and the answer, we'll look at this in more detail in chapter 14, actually, where we talk about the effect of electric fields on matter. There are charges on our skin because we have a layer of sweat, but we end up most of the time being electrically neutral. We have, the charges are sodium ions, so sodium +1, and chloride ions, mostly just salt. But, and in fact, inside our body we have lots of ions too, but we are mostly electrically neutral. Which means that the sum of all the charges ends up being 0. So just like a hydrogen atom is a proton and an electron traveling around it in this spherical pattern, the net charge is 0 because and that's a good thing because electric forces are really strong. And if we were actually negatively charged, we'd probably be stuck to something and unable to move. Oh, well, don't give up the dream yet. I mean, you know, harnessing the electric superpowers which combat the space witch spiders, because we did see some interesting things happening with that light bulb and the strangely shaped tube that got plugged in. So we'll find that there's some interesting things that could be done with charges, but it's a really good thing that we're not strongly charged because these electric forces are really big and we would be immobilized and attracted to other things. There's still hope, that's right. All right. So, okay, we have 3 minutes. That's not enough to do anything very exciting here. So for attendance, I'd like you to type in the chat window. What you think the most important or interesting idea we talked about today is. Okay, physics idea, not space spiders. I mean, you can add "and space spiders" at the end of your.
Dr. Chabay?
Yeah.
So I actually have kind of a question that's maybe a bit, if it's even on track at all, it might be a bit out of the scope of this course, but I was wondering, so we established that information can't travel faster than the speed of light. So does that, if there was like a source charge of a field traveling at the speed of light, is that source charge still affected by stationary fields
Well, first of
that it
all,
passes through?
the source charge could never travel at the speed of light. It could travel close to the speed of light. So for example, if you put it in a particle accelerator and got it up to a high speed, it could travel at some high fraction of the speed of light, but it can't travel at the speed of light. Okay, no object can travel at the speed of light. So that's a limit, but you can never get there. The only thing that can travel at the speed of light is light and information. Now, that charge is still a charge, so it's certainly affected by fields due to other charges. And it turns out that the shape of the field made by that charge is actually kind of interesting. As charges get moving, and this is discussed probably in chapter, it might be 17, but as charges get moving, so we have a positive charge moving that way, say, its electric field actually kind of gets squished up. So it doesn't look spherically symmetric anymore. It looks kind of like this. So the shape of the electric field for a very fast moving charge changes actually. But it's still a charge. It's still, its own electric field doesn't affect it, but other things' electric fields could change it, sure. And in fact, that's how we accelerate particles, by applying electric fields to them.
So does that mean that a particle in motion is affected by like a separate particle that is stationary? The particle in motion is affected by the field of the stationary particle before the stationary particle is affected by the particle in motion's field? That's a lot of...
No, they'd be the same. The delay is the same going both ways. The distance is the same. You know, so.
But isn't the stationary particle's field already there?
And the field of the moving charge is already there too. It's just what the stationary particle may actually see is the field due to where so here's our stationary particle, and here's our moving particle, okay? Okay, so this one's moving at speed v this way. We'll call this guy 1 and that guy 2. So it takes, so let's pick some time. Let's say, let me redraw this slightly. Okay, so that's 1. We want to know at this instant what each particle feels. So the field at location 2 due to 1, so we'll call that E1, is that way. So the force on this guy is going to be that way. At this location, what's the field due to particle 2? We want E2. Well, it actually doesn't point away from its current location. It points away from, if this is, say, 1 meter, it's sort of, the speed of light is basically a nanosecond per foot. So 1 meter takes 3 nanoseconds. Okay. So this actually hasn't found out yet that the particle is here, that particle 2 is at this location. It still thinks particle 2 is where it was 3 nanoseconds ago. Okay, so particle 2 was there 3 nanoseconds ago. So what it actually is going to experience is E2 from 3 nanoseconds ago. Okay.
Okay, I guess that was kind of my question. What I was thinking of was, is the particle 2 going to experience the, I guess, perpendicular force before particle 1 will experience like a perpendicular force? like
And that's why it's
perpendicular to
called
the velocity.
retardation, because the changes in the field take a certain amount of time determined by distance to actually catch up. So yeah, that's what it is.
All right, cool. Thank you very much for explaining that. That's really interesting to me for some reason.
It's cool. Well, it's just basically special relativity. I mean, this is an important piece. Yep.